basic characteristics of free vibrations of a material point. It's article number 11.1 from the book Mechanical Systems Calculations of the Marine Facilities. Let's consider a mechanical system consisting of the material point. Material point is the concentrated load, if we can neglect the sizes of the load, suspended by the spring to the support, to the fixed support. What could be the pattern of this load motion when it oscillates on the spring? The characteristics of the suspension is the force of the weight action on the concentrated load, the force of the elasticity acted on the same point. Just we neglect the sizes of the load, so we consider the material point of the defined weight. And the spring. The spring has the length and has a static deformation. So when the load not oscillates, so we so the spring experiences the static deformation delta S. And for this definite one, determination of the basic elements of the load oscillations on the suspension, on the spring, we neglect the resistance of the environment, so we neglect the aerodynamic or hydrodynamic resistance or just the friction, if perhaps the load experiences. So we consider the oscillations with not the resistance. The equation of balance gives us the equation of oscillation of material point. On the left side, we have the force of the inertia, the product of the mass of the material point by the acceleration. Acceleration second derivative by time of the coordinate x of the load motion. On the right side of the equation, we have the difference from the force of the weight, the gravity force acted on the suspended load, and have to remind that we neglect the mass of the spring. So just only we consider the mass of the suspended load. From this force of the load, which is a vector collinear with the direction of the coordinate axis x, we subtract the force of the spring elasticity, the formed spring elasticity. This contains as well as the force of the static deformation of spring, as well the force of the deformation of spring when the load oscillates. So the force of the weight of load is equal to the product of the mass of the load by the gravity acceleration is 9.81 meter per square second. And the force of the elasticity of the deformed spring is a product of the characteristic of the spring stiffness, C equal to the force action in the spring when we deform the spring per unit of the deformation. Unit can be any other dimensions of unit deformation, and the international system of units, the deformation units are meters. So C is force per deformation per 1 meter of the spring, and multiplied by brackets, in the brackets the total deformation of spring. This consists of the deformation, the ordinate of the motion of spring. We consider the point of the reference for the this one original scheme of the mechanical system in the figure 11.1.1a. The reference points we coincide with the point of the suspension of the load to the spring. Is neglecting the sizes of the load, the same point of the application of the force of the elasticity and the force of the weight of the load. And the distance of the motion of the point of suspension we indicate as x along the axis x or abscissa axis plus static deformation delta uppercase S as a static deformation of spring with not the oscillations of the load. Okay, and after the substitute of the forces of the weight independence on the mass and the gravity acceleration and the force of the elasticity of deformed spring onto the right side of the equation originally got the balance equation, considering the acceleration of the point and the forces of the inertia. We have final equation. We just simplify a little bit, transform this equation. For example, we divide all summands of the equation by mass of the load by m. So finally, we have just only factor 1 to the acceleration of the load x second derivative by time of its displacement along x-axis. So we have the linear second order homogeneous equation of the motion of the suspended material point on the spring or concentrated load on material point. So, and here we have the factor to the second summand k squared. K is the cyclic velocity of the oscillation. Cyclic velocity we can find as on one hand by the square root of the fraction of the characteristics of stiffness of the spring divided by mass of the load. Oh, this is equal considering the static suspension of the load here. As on the other hand, the force for the static suspension, the force of H equal of product of mass by the acceleration of gravity. Also static suspension, the load do not experiences the cyclic motions and do not experience the forces of the inertia, so just only the weight. And on the other hand, in the static approach, the deformation of the springs delta S and the force of the elasticity on behalf of deformed statically spring is equal to the force of the weight. So when we substitute instead of, if we multiply the numerator and denominator in the under the root sign by j is the acceleration of gravity. So after that, we will have that in denominator mass product by j is the force of the weight of the load and divided by c is equal to the static deformation due to product of the mass by the acceleration equal to weight on the other hand equals to the elasticity force when the statical suspension of load. And we have the same determination of the cyclic velocity, not only by the characteristic of the spring stiffness and its mass, but as well by the static deformation when the load suspended statical to the spring. Okay, we'll consider another two cases on the figure 11.1.2a when the load moves along the horizontal surface with no friction. So we consider the abstract concept of the oscillations with no friction resistance, with not resistance to the oscillations, and the motion of the load along the inclined surface, but as well with not friction, with not the resistance to the motion of the load. So when we consider the first one option, the balance is equal that the force of the inertia action equal to the product of the mass of the load by its acceleration equal to the elastic force of deformation of spring. So when we substitute instead of elastic force that this equal to the product of the stiffness characteristic of spring by the size of the motion, the ordinate of motion, abscissa, excuse me, abscissa of motion of the load. We can a little bit do mathematic transform to the left side of the equation. We will have the same equation as I originally had the mathematical equation. So for the horizontal location of the load on the horizontal surface, And in the vertical suspension by the spring, we have the same equation as x second derivative by time plus c characteristic of stiffness of the um, excuse me. Here we have to have the factor of m exactly, yeah, product by x, and characteristic of stiffness of the spring, and it is to be equal to 0. If here we have one factor, so here would be the k squared, the cyclic velocity, and powered by second degree. When a load moves along the inclined surface, as indicated on the second figure, 11.1.2b, the equation is the force of the inertia equal to the component of the wedge force on the direction of the motion of the load inclined. So the component is the product of the force of weight. This is diagonal of the parallelogram. Parallelogram is rectangular. So this leg in the right angle triangle is equal to product. This leg is horizontal component. Not horizontal, but the component parallel to the inclined surface of the wedge force. This equal to the wedge force multiplied by sine alpha. Multiplied by sine alpha. And the force of the this is component of the wedge force. And as well, along the inclined surface, we have the elastic force on behalf of spring. In this elastic force, the second component, elastic force, the second component here one, okay. Excuse me, static deformation of spring equals. So product of the stiffness characteristic of spring by the static deformation, as well equal to the component of the inclined component of the force parallel to the surface. So after substitute this to the after a definition of the static deformation by the sinus of the inclined surface, and finding that in the inclined position the force of the elasticity of static deformation of spring as well equal to the force of the horizontal to the inclined component of the wedge of parallel to the on the direction parallel to the surface are equal. So when we do the difference, subtracted the force of the elasticity acting on the inclined surface from the component of the wedge force parallel to the inclined surface, we will have the same after discovering the brackets, and we will have the same equation of the free oscillations with no friction of the load on the inclined surface. But let me please remind again, sorry for the error, here we will have k squared. If just we will have c, in this case we have to have here the product by m, by the mass for the acceleration. So let's consider here instead of c, but the k squared after the transformation of the equation. And so all this I have to underline that the mathematical equations of the free oscillations of the load on the suspension do not depend on the direction of the abscissa axis. It is is it vertical parallel to the axis of the spring, or it could be inclined for definite angle if the load with no friction moves along the horizontal surface under the action only the inertia forces and elasticity forces of the deformed spring, or along the inclined surface under the action of the same the wedge force and the forces of elasticity of spring. And this is in any case the this one linear second order homogeneous equation, differential equation. This equation has the general solution. Usually we consider this type of the solution of the second order linear homogeneous differential equation, this type. This consists of two summands. First is any constant we have to find using the initial conditions multiplied by cosine k with the cyclic frequency product by t, plus the second summand, the next constant multiplied by sine of the kt. So to use the initial conditions to find these constants, as usually we have the assigned for definite time moment could be the time equal to 0. We have the initial location of the load and the initial velocity of the load. To find these two constants C1 and C2, we have to have the mathematical equation as a general type of the for the velocity. Velocity is the first derivative of the characteristic of abscissa of motion. The first time derivative is minus c product by kk comes from the equation under cosine, and product by sine is cosine derivative by t is minus sine, plus e2 multiplied by k comes from the under the equation under the sine, and derivative of sine is cosine. So we have two equations for the motion of the point and for the velocity of the motion of the point. After that, we can use the initial conditions. At the time equal to 0, the motion, the characteristic abscissa of motion of the load equal to x0, and the initial velocity equal to v0. After the substitute this all to all three characteristics into the general type of the solution, into this equation, to this one, we decided the system of the equations, and we can find that the constant C1 equal to x0 and constant C2 equal to the initial velocity divided by the cyclic frequency. And after the substitution to the general type of the decision of the second order linear homogeneous equation, we can find its solution in the type of the products of the initial location of the load when the time was 0 multiplied by cosine k by t, and plus the second summand is the initial velocity divided by the cyclic frequency. Cyclic frequency we have decided the when we do transform the equation of the balance of all forces acting onto the load on suspension, we have the characteristic of the cyclic velocity. Let me remind is the product as a product of as a product of cyclic velocity as a fraction of the characteristic of stiffness of the spring divided by mass of load, or as the square root of the fraction of the gravity acceleration g divided by static deformation delta s. So this is in the got decision of the derivative differential equation. And besides, we can find another one form of this equation as of the decision of the linear homogeneous equation, second order. This could be the form like x, the abscissa of the motion of the load, equal to the product of definite amplitude of the oscillations, we say A, product by the sine, within the brackets in the sine, we have the k multiplied by t, k is the cyclic frequency, and the initial phase of the oscillations, we say initial phase characteristic within the under the sine of the equation, mathematical equation, as in the sign of argument of the sign. And how we can find it? So the main elements of the oscillation is the A. We can find as we, if consider A, the for the maximal magnitudes of the sine function, cosine function, we can find like C1 equal to A. When we substitute this to the this mathematical equation, we can find that we can use the Pythagorean theorem, Pythagorean formula to find what is the amplitude of the oscillation. Amplitude is the square root of 2 summons is the initial location of load squared plus the fraction in the numerator is squared initial velocity of load divided by squared cyclic frequency of the oscillations. And besides, after the substitute these two formulas into the got mathematical equation. So considering this mathematical equation, and we compare to the second one, we can find that initial phase of the oscillations equal to the difference to dividing the amplitude of the first one summoned to the amplitude of second one summoned. If we divide amplitudes of this of the summons in the first got type of the decision of the second order linear homogeneous differential equation, we will have the tangent of the initial phase of the oscillations is the fraction in the numerator. We have x0, the initial location of load, multiplied by k, the cyclic frequency of the oscillations, divided by initial velocity of the load. And besides, we considering the shape of the function characterizing the free oscillations of load, and the abscissa axis we indicate t time, the dependence on the abscissas of the location of the load suspended by spring to the support. And this we have the trigonometric function, and with a period t. Period t is a period of free oscillation. This equal to 2 multiplied by pi divided by k cyclic frequency. So we have dependence of the, and if it, so in this case we have what is a period of the free oscillations of the suspended load. And let's consider the assignment. The load begins to move from static position of balance with initial velocity 1 meter per second. On the figure 11.1.4 is shown the suspension of the load which has the initial velocity 1 meter per second exactly along the axis x. The axis x we coincide with the for the first one decision, we will have 2 options of decision of this assignment. Let first assign the reference point of the motion of the load with the point of location of the load characteristic for static deformation when the load suspended statical to the spring. And other assigned elements of spring. The spring has the length of 30.2 centimeter. The static deformation of spring is 9.81 centimeter, or is in the meters 9.21. The multiplied by 10 to the power minus 2. Next, we consider the balance equation. On the left we have the force of inertia, on the right we have the difference of the force of the elasticity of the form spring subtracted from the force of the weight of the load. And next we assume as well the gravity acceleration, And we can convert the original equation, this one equation, we will convert to the indicated type, and we will consider that the wage of this one wage P force of the suspended load equal to the elastic force on behalf of the spring in the static location of the load. So we can do the mathematical transform of the first equation, and we will have the linear usual as we considered before for the general approach, linear equation of the linear second order homogeneous differential equation of the motion of the suspended load. This, let me remind, relative the reference point 0, 1. 0, 1 reference point corresponded to the static deformation of the spring, so with not oscillations, 0, 1. And first we can determine that the cyclic velocity, considering the static deformation of the spring, equals to 10 seconds in the degree -1. And the resulting law of the motion of material point suspended for the first way of determination of it equals to, considering the having the first derivative which correspond to the velocity of the motion of the suspended load related to the reference point equal to the point of suspension, static suspension of the load. We consider initial data that at time equal to 0, the deformation equal to 0, the initial deformation of spring equal to 0, and the initial velocity equals to the v0. So after it substitute onto the equations for the location of the load along the x-axis and along in the equation of the velocity of the load along the x-axis, we can get the constants of this equation, the constant C1 equal to 0 and the constant C2 equal to 1/10, so 0.1. And thus the law of motion of material point is, when we substitute this all to the C2 we have, to the second sum of the first will be 0, as C1 is 0. So we will have that the pattern of the motion of the suspended load is equal to 0.1 product by sine 10 multiplied by t time meter, the international system of units we use. And this is referred to the point of suspension. The point of reference we coincides for this the first way originally to the point of suspension, static suspension of the load with not oscillations. So if we as well will consider the location of this point of the reference relative to the point of the suspension of spring itself, because it is assigned to find the pattern of the motion of the load relative not the point of the suspension of load to the spring, but the spring to the support. This is the reference point have to be. We just only use the another one reference point to decide the linear homogeneous, to define and to decide, to draw up and to decide the linear homogeneous second order equation differential of the motion of the load. So we as well have to find the static location. Static location is the length of the not deformed spring and plus static deformation of spring, exactly. And this is 40 centimeter. And we finally have the resulting law of motion of material point on the spring in the form of 0.1 product by sine in the brackets 10 multiplied by t plus the constant 0.4 meter. This is the another way. We can originally consider the reference point as a point of suspension. So what is the difference of the decision? The second decision is if we move the reference point to the suspension, if reference point is not 0, 1, but 0. So x in the second approach we will consider from the reference point of 0. In the first we did in the reference x1 relate to the reference point of the location of static suspension of the load. Exactly. What now if we consider the variable x originally? So oh yeah, sorry. So we can find that the coordinate of location of the load is equal to the coordinate of abscissa of its motion when oscillating plus static deformation plus the length of the not deformed spring. And the elasticity force acting on the load is the product of the stiffness characteristic of the spring by the brackets. In the brackets we have the location of the load considering static deformation and the motion, the load deformation, minus the length of spring with no deformation. So this is total deformation in the brackets of the spring, and this is elastic force. And when we substitute this all into the equation of balance, on the left we have the acceleration, the force of the inertia, here we have the wedge force, and here we have the force of the elastic force when consider the variable x abscissa variable of the motion of load relative to the point of suspension spring. This is the equation if we substitute this all into the when I substitute instead of the variable the equation of the variable considering the static deformation length of the not deformed spring and the motion of the load when oscillating. And what is that? That it is the second order linear differential equation, but this is not the homogeneous equation, but this is inhomogeneous, as on the right hand we have definite constant. This constant do not contains the variable x, variable motion, dependent on time, but this is a constant. Anyway, this is not the homogeneous equation. And as we remember about finding the decision of the inhomogeneous equations, yeah, as we can consider the Cauchy theorem of the decision of the differential equations as the decision of the differential equation consists all decisions of this equation. And in definite one case, this consists of two decisions. The first is x1 and the second x2. X1 is the type of decision of general decision of the appropriate homogeneous equation, and the second one is the type of the particular decision of the inhomogeneous equation. The type of decision of homogeneous equation we considered before, the product of two summands, which the first one is a cosine function, second one sine with a constant and the cyclofrequency. And the type of the inhomogeneous equation too is a definite constant. So we usually consider the decision, the particular decision of the inhomogeneous equation the same type as we have the right side of the inhomogeneous differential equation. So the right side is definite constant, this one definite constant. So as that we have to look for the decision, the particular decision of the inhomogeneous equation. This inhomogeneous equation, we need to find this particular decision. If equal to 0, this would be homogeneous. In this case, we have to find the general type of the decision. This is 1. And besides, we have to put into the second summand in the final decision of the equation, we have to put the second summand x2 is a particular decision of this one in homogeneous equation. And this is constant on the right end of the Got equation of the Got differential equation of the motion of the load on the suspension. And this is equal to A. Yeah, and after the a displacement set of displacement of velocity for the initial conditions. Here we have it. The constants we have as we have that, and the second summand is A. A is equal to, if we at the time 0 we have the general decision as the cosine of 0 is 1 and the sine of 0 is 0. So 1 product by C1, C1 is 0. I am talking about the a particular decision of the inhomogeneous equation, and the second summand C2 product by sine of 0 is 0. So the inhomogeneous equation is just A, the same, and A is a total of the length of the spring with no deformation plus static deformation of spring as well. And we substitute that x2a into the second summand of the finding decision of the location of the load. And we have C2 for the general type of decision of the homogeneous equation, and C2 equal to 0.1. And finally, we have the common decision consisting of two summands, plus 0 for the plus x2. The first is the general decision of the second order linear homogeneous equation, general decision. So that is another optional decision when we coincide the point of the reference to the suspension of the spring. This is the same as we coincide originally the reference point with the point of the static deformation of spring. But after that, for the first one, we as well consider the static deformation. On the second one, the static deformation corresponds to the particular decision of the inhomogeneous equation, due to the right side of the equation is constant. And questions and comments. 11.1. The action 11.1 the action on material point, the considered load, or on body, or on element of mechanical system of internal forces proportional to acceleration, the second derivative of displacement with respect to the time parameter, and the forces proportional to displacements, the elasticity, the forces excess buoyancy when immersed in liquid, etc., leading to solutions in the form of harmonic oscillations. Yes, it is the general type of the balance equation of the load suspended on spring or located and under action of the weight, irrespectively, is it the just suspension in the space or the force located on the surface with inclined or horizontal surface with no friction. If in the case for the free oscillations, we don't consider the resistance of the body motion. So this balance of the forces of the inertia and the elasticity of the spring gives us the general equation. Usually this is second order general homogeneous equation of the differential equation of the motion of the load suspended by spring. 11.1.2 equation of oscillations of material point without the environmental resistance and solution of this equation. The equation is on the left hand usually the inertia force, the product of the mass of the suspended load by the its acceleration. Acceleration is the second derivative of the abscissa of the displacement, and second derivative equivalent to the acceleration of the point, derivative by time. And on the right hand of the equation, we have the difference from the force of the weight acting on the load. We subtract the force the restoring force of the elasticity of spring, which tends to return the load in the location of the suspension with not oscillations. And to decide this equation, first we have to transform this, not difficult, to the usual type of the second order linear inhomogeneous differential equation, and we have the type of decision of this inhomogeneous equation as just a total of two summands of the oscillation functions like sine function, cosine function with definite constant factors. These factors we have to find using the initial assigned or got initial conditions of the oscillations. 11.1.3 circular, the cyclic frequency of ray vibrations of material point, the dependence of cyclic frequency on the characteristics of rigidity and the mass. Yeah, the cyclic frequency when deciding the homogeneous second order linear equation of the oscillation of the suspended load or material point with the wedge, the frequency equals to the factor of the transformed second summand in the equation or the indicated equation. I talked about this, the second order linear homogeneous equation, and is equal to the square root of under square root we have the fraction, in the numerator we have the stiffness characteristic of spring, and the denominator we have the mass of the suspended load, and the square root as well we have. Or this equals to the square root of the fraction, in the numerator we have g is the acceleration of the gravity, and the denominator we have static deformation of the spring if we assume the suspension of the load with not oscillation. So this all two gives us cyclic velocity, cyclic frequency of the oscillations. 11.1.4 integration constants of the evaluation of oscillations, the determination of initial phase of oscillations and initial amplitude. When we substitute the initial conditions in the equations, in the got equations of the general type of the equations, of which are the decision of the linear second order homogeneous equation, differential equation of the suspended load motion. When we substitute, we have the general type of the decision, and this is a general shape, general pattern of the motion of the load suspended, and we can find as well the general pattern of the velocity change in time, just to find in the derivative of the motion characteristic along definite abscissa of the motion. Time derivative is equal to the velocity along the abscissa axis. Then we can use this to find the integral constants if in these two equations we substitute the initial conditions. And after that we can find the phase and the amplitude of the oscillations. Considering the amplitude we can find due to the Pythagoras theorem as the square root of the constant got C1 plus constant C2. And the equation due to the two summands are orthogonal in the mathematical sense. Two summands in the general type of decision of the second order equation, linear homogeneous. And we can use to find the amplitude the square root of these two constants squared, both in total. And besides considering the proportion between the constants, we can find the initial phase of the oscillations of the load suspended to the spring. Thank you.